So today's lecture is about full subtractor and look ahead carry adder. Now in the previous video we have talked about half adder, full adder and the circuit realization, that is the logical circuit. Okay, my name is Shiv Charan Puri. I am from EC department, Asansol Engineering College. Let's start. So let us talk about half subtractor at the beginning. Half subtractor is employed for subtracting two single bit numbers. Half subtractors does not take into account borrowing from the previous circuit. To overcome this drawback, full subtractor is employed for complete arithmetic subtraction, which we will be discussing in the succeeding slides. Now in half adder, there are two inputs A and B, as it is 2-bit subtraction, and this is logical circuitry. It produces difference and borrow. Now let us talk about the rules. Okay. So rules for binary subtraction. Okay. So you can see here 0 minus 0 is 0, 0 minus 1 is 1 with borrow 1, 1 minus 0 is 1 and 1 minus 1 is 0. Now let us look at the truth table. So for this 2-bit operation, you can see here 0 minus 0, it produces difference 0 and borrow 0. 0 minus 1 is difference 1 with a borrow 1. 1 minus 0, difference is 1 and with the borrow of 0. And 1 minus 1 is 0 for the difference and 0 for the borrow. Now let us go for the K-map simplification. Okay. As you can see here, this difference is valid for 0, 1 and 1, 0. That is 1 and 2. So if we go for the K-map, that is a 2-variable K-map, where we put these 2 bits A and B. So this is a 0 place and this is a 1 place. Similarly, here this is 0 place, this is a 1 place. So 0, 1, that is the first decimal point. We have 1 over here, and 1, 0, that is 2, which we have seen over here. You can see here 1, 0 is 1 for difference. So we get here 1. Okay. So when we see it is not making any pair over here, so we have to go for, individually. So it produces D. For this one, it is nothing but A bar B, and for this one it is A B bar. A bar B plus A B bar, which is nothing but A XOR of B. For borrow, similarly, we have seen borrow is valid only for this two, this combination, that is 0, 1, that is A bar B. Say you see here, as it is not having any of the valid cell over here, so there is no pairing, and eventually we only get from here borrow as A bar B. See here. Now let us go for the logical circuitry. As you can see here, T, it is produced by, this is XOR logic. Okay, this is XOR gate. So it will produce D is equal to A XOR B, which is satisfied over here. And similarly, it produces borrow as A bar, as it is, as there is a NOT gate over here. So it is A bar into B, because here it is a AND gate. Now if you wish to obtain the result using basic gates, that is only by using the AND or NOT gate, you should go with this type of circuit diagram. It is easy to use, and I will always rather advise you to choose this kind of line diagram. Okay, where one is, you put one line as A over here, take an inversion over here, which will produce A bar. Here will be A bar because it will be inverted. You take another line B and you take B bar. It will be fairly simple to use in the result side, because we know D is equal to A bar B plus AB bar. So take an AND gate. You see here an inverter, and this is AND, this is OR, and this is AND again. So therefore, you can see here, if you put one AND gate over here, so here you will get A bar into B. You can see here. Similarly, you will get here A into B bar. You see here, and here you will get A bar B. So this is given by this is the expression for carry, and if you OR this both, you will get D is equal to A bar B plus AB bar, because it is a OR gate over here. So you can also construct this half adder expression using basic logic circuitry or the basic gates. Now let us talk about the full adder, a full subtractor, I'm sorry. So full subtractor is a combinational circuit. It performs subtraction involving 3 bits: minuend bit, subtrahend bit, borrow from the previous stage, which was missing in the half subtractor. So as you can see here, it has three inputs. Okay. Now it produces 2 output, D difference and borrow B out. Okay. You can see here the truth table. Okay. So 0 minus 0 minus 0 is 0, borrow, and 0 difference. 0 minus 0 is 0. What you can do is because it may be confusing over here. So what I will suggest is you just look at this 3 bits in this manner. So A minus B. So 0 minus 0 will produce in the middle intermediate state difference 0 and borrow 0. Okay. So then 0 minus, then with this result, difference is how much? 0. So 0 minus 1 is how much? 0 minus 1 is difference 1 and borrow 1, and you will get substitute over here. Again going 0 minus 1. So difference 1, borrow 1. Difference 1 minus 0 is 1, 1, same. 0 minus 1, difference 1, borrow 1. Difference 1 minus 1 is how much? Difference 0, but borrow was 1, so it will be here set. 1 minus 0 minus 0, it's simple case, 0, 1. Difference is 1 and borrow is 0. 1 minus 0, 1, borrow 0. 1 minus again 1 is nothing but 0, 0. Okay. 1 minus 1 is how much? 0 with the borrow 0, and 0 minus 0 is 0 with the borrow 0. 1 minus 1 is 0, difference is 0, and borrow is 0. Okay. So difference 0 minus 1 is how much? Again 1, 1. So in this way you can just put down the whole of the combinations in the truth table. After that, there is a requirement for you to simplify it. So just to look at this expression, you can see this expression D is equal to, it is valid for this combination. Okay. So it is nothing but A bar, B bar, B in, A bar, B in bar for this one. Or rather you can also say like that, if you just want to go with the min terms, it is nothing but summation of small m, that is min term, 1, 2, 4, 7. So summation of m of 1, 2, 4, 7, and straight away we will go to the K map. So for D you can see here, this is 0, 0, 0, 1, 1, 1, 1, 0. So you can see here 0, 0, 0, 1. So this is 1, this is 2, this is 4, and this is 7. Okay. So as you can see here, nothing you can pair over here. So individually you have to go, and when you solve it, you will get D is equal to AX or BX or BN. Okay. So for the borrow part, okay. So for the borrow part, you can see here borrow, you can write down B out, summation of small m, 1, 2, 3, 7. Okay. So you can see here, so 1, 2, 3, and 7, and clearly you can make 3 pairs over here. Okay. So if you look at this pairing, this is dual. Okay, so row into column. So here this row is simply a bar. So there is no need of any calculation for this particular point. I mean for this particular pairing. This pairing is because of this row and these two columns. So row into column. So row is established, it is a bar. For column, it will be B. You can see here 0 1 1 1. Okay, so 0 1 1 1. So B bar and B, you can see here the opposite one, opposite, and here is the non-inverted form and here is the inverted form. It will combine, it will produce 1. So the rest will be only B in. So it will be row into column, that is A bar B in. A bar B in. You can see here clearly it is reflected over here. For this dual, for this pairing, same, this row, and for this two columns, I mean this pairing is because of this row and these two columns. Okay, so for these two columns, B in bar will be gone. So the rest will be only B. So it will be A bar B. A bar yeah, A bar B, yeah, you can see here it's reflected over here. So for this pairing, for this dual is because of these two row and this column. So this two row is opposite one, A plus A bar is 1, so it will be gone. There will be nothing in the row into column, 1 into this column, this one, it will be BB in. You can see here BB in is reflected. So if you sum it up, you will get the expression like this. Now the rest is only the logical circuit. You can see here T XOR gate is there. Just take out the line diagram connections and clearly you will get the difference at the borrow part, which is fairly easy to draw. Now let us talk of the ripple carry adder. Okay, so in ripple carry adder, each full adder, okay, the ripple carry adder, each full adder has to wait for its carry in from its previous stage. Full adder. Thus, nth full adder has to wait until all n-1 full adders have completed their operations. This causes a delay and make ripples carry adder extremely slow. The situation becomes worst when the value of n becomes very large. To overcome this disadvantage, carry look ahead adder comes into play. Now, you see here from we have talked in the previous video regarding the parallel ladder. Okay, in parallel ladder we have seen the carry out of each stage is connected to the carry in of the next stage. The sum and carry out bit of any stage cannot be produced until sometime after the carry in of that stage occurs. Why it is happening? This is due to the propagation delay in the logical circuitry, which will lead to a time delay in the addition process. The carry propagation delay for each full adder is the time between the application of the carry in and the occurrence of the carry out. Okay, so if you just want to sum up, there's a total sum, there is a parallel output is not valid until the cumulative delay of all the adders. Okay, so let us see how we will overcome this. You can see here this is a 4-bit ripple carry adder we discussed in the previous video. You can see here. So all the succeeding adder circuit are dependent on the previous carry, which makes it very hectic, and there's a lot of delay for getting the entire output. So let us now talk about the carry look ahead adder. Okay, so carry look ahead adder is an improved version of the ripple carry adder. Now it generates the carry in of each full adder simultaneously. That's the key, without causing any delay. As you can see here. Now, in the case of the parallel adder, the speed with which the addition can be performed is basically governed by the time required for the carries to propagate or ripple through all of the stages of the adder. The look ahead carry adder speeds up the process by eliminating this ripple carry delay. Okay, it examines all the input bits simultaneously and also generates the carrying bits for all the stages simultaneously. Now, therefore, the method, this method of speeding up the addition process is based on two additional functions of the full adder called the carry generate and carry propagate function. Okay. See here, see here. So in this diagram, as you can see here, this is the 2-bit AIBI any stage, and this is the carry in from any stage. Okay. Okay. Any stage means the previous stage. Okay. Now it will produce. You can see here in this circuit the two internal signal Pi and Gi are given by, you can see here. So Pi is equal to this XOR this. Okay. And Gi is equal to Ai into Bi. Okay. This is intermediary. Now again, this, that is Pi XOR Ci, is again Si, the final stage, and Pi and this one is again carried out here to get the next stage carry. Okay. So in this circuit, the two internal signals which is given by this two expression, Pi is equal to Ai XOR Bi and Gi is equal to Ai Bi. Okay. So the output sum and carry can be defined as Si is equal to Pi XOR Ci. Okay. And Ci plus 1 is equal to Gi plus Pi Ci, as it is very evident from this figure. Okay. As you can see here, Gi, which I told you is known as the carry generate signal, since the carry Ci plus 1 is generated wherever Gi is equal to 1, regardless of the input carry Ci. Pi is known as the carry propagate signal, since wherever Pi is equal to 1, the input carry is propagated to the output carry, that is Ci plus 1 is equal to Ci. Now we should note that wherever Pi is equal to 1, Gi is equal to 0. Okay. The Boolean expression for the carry out of various stages can be written as, you can see here. So we have only taken here from C1 to C4. So C1 is equal to G0 plus P0 C0. Okay. C2 is equal to G1 plus P1 C1. Now what we will do, now this is how it is calculating simultaneously. Now you can see here, just what we'll do, this C1 expression just put over here, and finally we'll get this one. At the next stage, you can see here it is taking care of all the previous two carries, and in the final stage for the C4, as you can see here, it is taking care of all the previous carries, you can see here. So therefore it is very quick and all the carries are calculated at once. Thank you.